Right, thanks everybody for being here. This is another talk in the series about of the Autonomy Talks, and today we have Dr. Saverio Bolognani. Saverio is currently in the Automatic Control Laboratory with Florian Dorfler here at Zürich. He got his PhD in Padua, so he's very connected to all the many very good Paduan people in control. I met him actually at MIT when he was doing a postdoc with Munzer Dalle. And then it so happens that as we moved here, he also moved here. So we've been synchronizing for a bit. And also Saverio is a co-advisor of two of our students, Alessandro Zanardi and Erzat Elot. Today is going to talk about power systems. Please, Saverio, the stage is yours.
Thanks a lot, Andrea. Yes, I'm going to talk about power systems. On the other end, as you can see from the title, there's two components in the talk. There's autonomous optimization, which I would explain what exactly I mean with that. And there's power system operation, which is the application I have in mind. My idea for this talk would be to, and it's difficult to present the two parts separately, so I go back and forth between the method and the application. But ideally, by the end of the talk, I would like to convince you that the method maybe has more potential than that specific application. And here, if you have any opinion on that or any idea about that. But yes, the presentation would also be, the strong motivation for us was real-time power system operation. And I will start by explaining exactly what we mean by that. By the way, if you have questions during the talk, as it's a little bit longer than the usual talk, I'm keeping an eye on the chat. Feel free to write your questions. Or interrupt me. I will try to address those. Okay, so what's the problem, or what's the new challenges in future power systems? Most of you probably know it in a way or another. I'm assuming the background is a bit mixed, so I will cover it quickly. Most of the renewable generation that people are trying to connect to the grid is unpredictable in nature. Like we kind of have methods and tools to predict the solar irradiations, wind, biomass production, hydro production. I mean, some of it is controllable as well, but there is some uncertainty. And this uncertainty is not the kind of uncertainty that if you have a lot of generators, the uncertainty disappears. This is correlated uncertainty. On the other hand, this kind of generation happens to be very flexible in terms of controllability. Compared to traditional generators, power converters that are used to connect this kind of energy sources are fully controllable, are much more controllable than an electromechanical device in some sense. And the third challenge / opportunity for the system is electric mobility. Not from the point of view of the autonomy in mobility that maybe you are more aware of, but from the point of view of the energy demand. Right now, the entirety of transportation electricity demand comes from, is served by primary fuel like gasoline, right? If this is moved into the electricity domain, so to the right of this line, then you would expect quite a substantial load on the power systems, and a kind of a strange one because it's moving and it has some very peculiar patterns in time and in space. Okay, so how does the grid cope with this uncertainty, or at least with the uncertainty that is present right now in the grid? So the power system operation is done in multiple timescales and in some sort of hierarchical structure. On this low end, there's what is called the optimization, optimal power flow optimization. Optimization stage is the stage of the system where the operator decides which generators to dispatch based on usually purely economical reasons, like different sources have different costs, but they are more or less predictable. And so, there's a mixture of generators which hedges against the uncertainty at the lowest cost. This is something people in power system are good at. I mean, this is done typically the day ahead. A schedule is prepared, so that's what is actually used later on, and that's simple. It's a pure optimization problem. On the other end of the system, there's the fastest part of the system, what is these low-level automatic controllers. This is something that happens really at the individual generators, and it's in the squarely in the realm of control systems. This is feedback, like you measure frequency. Frequency is telling you if there's power imbalance, and based on this measurement, you decide whether to ramp up or ramp down power generation. No communication or almost no communication, very simple controllers, and controllers that are tuned, with some vast, kind of large margin of robustness, right? Things are needs to be robust at this level. So what's in between these two levels? It's what is called the real-time operation. And real-time operation is any mechanism that is in place to take care of unforeseen deviations from the schedule. Things that the low-level automatic controllers cannot do. Okay. This seems to be like a marginal problem, or let's say some sort of one piece of the puzzle, but it's actually quite a relevant one. So if you look at how it's done today, this is now done basically with humans in the loop. Like it's an operator mediated activity where operators need to look at the state of the system, decide what remedial actions to take. And this is not always, this is getting more complicated now that uncertainty is increasing. And in fact, if you look at the money that is spent into this redispatch and the number of actions that needs to be taken, this is growing in time. So this is a little bit old data. I apologize, but new data confirm the trend. This is getting inefficient. And I mentioned only power balance, but the reality is a bit more complicated. So for those of you that have a bit of a background in power systems, under the same umbrella of real-time operation, you could imagine voltage regulation or voltage collapse prevention, line congestion relief, reactive power compensation. These are separate ancillary services. Right now, they are only partially automated, and they are provided by different mechanisms, not by a unified approach. And our view, and the view in the project that is actually funding most of this research, is that future power system will require better tools than this. We require some online monitoring and some automated tools to make sure that specifications of the system are met in real time when things go a little bit outside of the predicted path. Let me just give you, I'm not going to present many simulations, and this is just considered as a teaser. So I won't go into the details of what is here, but I want to motivate and at least convince you to pay attention for the rest of this talk. This is a transmission system from a Nordic system like Sweden and Norway. And it's a very tall system, right? Because the country is very long. And so there's what happens is that each of these buses here corresponds to generators and loads and controllers, those local controllers that I described before. Now, the long lines that you see here between the central and the north and the south are actually really long lines because they connect the north to the center to the south of Sweden and Norway. And what happens is that this system is relatively prone to voltage instability. So for example, if you increase a little bit the load in one particularly weak point of the grid, then what you could see is that all those automated mechanisms, they kick in place and they start acting, they try to fix the problem in an automated way, but it is not enough. They typically get to saturation, and then there is a cascade of saturation and nonlinear dynamics, and then there's voltage collapse, which will be a blackout. Okay, so how does a proper real-time optimization look like in such a complicated scenario? Well, we implemented the controller that I'm going to present you later. So for now, take it as a black box, and this is what happens. Okay, so here we were able to control inputs of some generators, and we were able to avert the voltage collapse. Now, whether this is a difficult or easy task, I didn't give you enough information to tell, but I want to show you that the remedial action was a very complicated one. So if you look up here, what we had to do is to change set points for basically all the generators, and not even in a uniform way, right? Some of them we had to lower the voltage reference, for some when we had to raise it. And it's something that they would argue an operator cannot do, right? And this had to be done in, the x-axis is seconds, okay? Okay, so with this in mind, I will try to, from this example to recognize or identify what makes a real-time operation effective. Well, there's a number of features that we would like to observe, which come from optimization. I called it here feed-forward optimization, because this is the optimization where you take an estimate, you solve an optimization problem, and you give commands to the system, and then you observe what the system does. And some nice features that we would like to take from feedback control, which is what I described on the faster timescale, right? You take measurements, you compare it with the reference, and you decide how to act on the system. So from feed-forward optimization, the main advantages that we would like to maintain are the fact that you can take very complex optimal decisions. Like you give me a cost function that you would like to minimize, and I can design a solver. You give me constraints, I can include the constraints. If you have multiple inputs, multiple outputs, that's fine. I mean, the high dimensions of the problems are tractable to some extent, right? The main problem is that is a very highly model-based approach. You need to trust your model, and it could be computationally intensive. In feedback control, the positive part is that this is very robust to model uncertainty. Actually, most of these controllers are designed without a model for the grid, with only a model for the individual device. And the response is quite fast. The problem is that this is not solving a complex decision problem. This is tracking a reference. And this is definitely not enough. Operation is suboptimal because there's no notion of optimality. And including constraints is possible, but it's not typically done. It's not completely trivial, and it's not done in practice. So what I'm going to present today is this autonomous feedback or feedback optimization approach to the system, which ideally has the best of these two words. So the things you see in red. I'll show you, and then you tell me if you think we got it right. Okay, just one slide about the position of this kind of work in the literature. For power system operation and some other infrastructures, this is a relatively recent effort. I would say the very first works maybe in 2013, and then quite more recently for the rest. Similar approaches have been have been explored before. I want to mention two in particular. One is process control, which was a relatively old stuff. You can see from the dates, mostly because this was for slow systems. So in slow systems, people wanted to optimize the output of a chemical reaction, and I think similar things have been done there. And another thing that it's worth mentioning is congestion control and communication networks. Even here, people have not really designed, but reverse engineered communication networks and some mechanism in communication networks as a feedback optimization routine. I can elaborate a bit if you have questions at the end, but this is just to put a little bit of perspective here. Okay, so I'm going to touch 3 points. The first one is definition and a bit of analysis of closed loop trajectories of a power system on the power flow manifold, which I am to define. The second point is the interconnected dynamics. So what happens when I take my controller and the plant dynamics and they connect them. And the third point is just a comment on possible future steps, and both in the theory and in the application. Okay, so let's start from, if you have any question now, it's actually a good time. If the motivation is not clear, or if anything is requires some clarification. Okay, so let's start from the closed loop trajectories on this power flow manifold. Almost everything in here needs to be defined a bit. So the model of the system, of a power system, is quite well understood. So if you take a power system, a power grid, the state of the power grid is given by voltages at every bus and power injection at every bus, so at every node of this graph. These quantities are both complex numbers because you have to, at steady state, these are sinusoidal signals, so you need to encode both the amplitude and the phase, but this is not critical here. You have a state which is represented by voltage magnitudes, voltage phases, active power injection, reactive power injection. These quantities here, they need to satisfy very standard and very basic laws from physics, Ohm's laws and Kirchhoff laws. These can be combined together. What you get is a set of nonlinear power flow equations. Now, the steady state of a power system needs to satisfy this one no matter what controller you are applying, right? This is literally the physics of the power lines connecting the different parts of your power system. Okay, so we start from this model. Now, these, if you define the state, as in here, as voltage, magnitudes, phases, active and reactive power injections, then we don't need to keep track of the complexity of these power flow equations. We can just call them f of x is equal to 0, okay? The thing is that the set, you can prove that the set of all points, states of the system that satisfies power flow equations constitute a manifold of dimension 2n. N is the number of buses in the system, okay? So this is the first observation, which is key for the rest. States, the subset of states of the grid which are consistent with the physics have this nice mathematical structure. The main reason why we like this mathematical structure is that you can talk about trajectories on a manifold. Why? Because the constraints or the requirement that you have on trajectory to remain on this manifold, so to be actually trajectories of the power system, is that the velocity of the trajectory, so x dot, is tangent to the manifold. So because this is a manifold, it's a regular submanifold, the tangent is well defined everywhere, and you actually have a closed form expression for that. Okay, so that's the first observation to make. So because we want to steer the system around, but we want it to be consistent with the physics with the laws of physics, we need the state to remain on the manifold during the trajectory, which means that x dot needs to be tangent. And for the tangent space, we have a closed form solution, which I'm not representing here, but it's function of the parameters of the system. It's an implicit representation. So this is a representation of this kind here. But it's also very tractable. It's sparse, it's structure preserving. It can be used for approximations. We're not going to use it for approximations here. We're going to use it because we want the trajectory of the system to have a velocity which belongs to this tangent space at every time. Okay, so now we know what is our space where our system is moving, right? This manifold. How do we define a control problem on this space? Well, we use the language of optimal power flow that I presented before. This is a language from optimization, but it's useful here. What typically optimal power flow representation is the one you see here. You want to minimize some economic cost, some generation cost, subject to a number of constraints. The second one here being power flow equations. So this is the manifold constraint, and all the rest being some operational constraints, like there's a maximum power you can inject, there's a maximum voltage you can admit, there's a maximum current on the lines that you can admit, these kind of things. Notice that this is only the solution of this optimization problem is one specific point of the manifold before. Now, we don't want to solve an optimization problem. We want to solve a control design problem, but this is our specification. So what we would like to do is to design a controller that gives some inputs to the system, receives some measurements on the systems, and once it's in closed loop with the physical system, so with the power flow equations, gives you a closed loop trajectories, which is on the manifold at all times, satisfies the constraints at all times, and converges to the solution of the OPF. So in a way, we want to design a solver for this optimization problem, but it's not a solver that can do everything, like backtracking, trying different solutions, leaving the feasible space or anything like that. The iterations of the solver needs to be actually a trajectory of a physical system. That's the core idea. From now on, all this notation, I was fast on the notation mostly because you don't need to remember it. We will use a prototypical representation of this power flow. Cost function is phi of x. The state x needs to be in calligraphic k, the constraints, which is intersection of the manifold and the operational constraints, calligraphic x. You really don't need to remember anything else. And even these terms here, I will recall them later. Okay, so but that's what we are trying to do, to solve an optimization problem of a manifold with a trajectory being the trajectory of a physical system. Okay, so I have to say the trouble from this optimization, from this control design problem, comes from the constraints. The cost function is typically basically almost trivial, but the constraints are complicated beast. Typically, these constraints come from the physical saturation of devices, the saturation of controllers, some specifications given by the operator, which are strict. These constraints can be time varying. And then once you have all these operational constraints, you need to intersect them with the power flow manifold. And what you get is an object typically similar to this one. So the feasible space for your system, for your dynamical system, it's a manifold that has been cut and sliced by these constraints. This creates some challenges. So for example, sometimes it creates disconnected component. There's a relatively famous paper from 2016 where they show that actually the optimal solution to the OPF could be in a region disconnected from the region where you are now. And so you need to be careful. If you want to go there, you really need to make sure there is a trajectory that can take you from point A to point B. You cannot just tell your generators that this is the optimal one, just try and go there, because there's no way to get there safely. So what we need, and that's what I would spend the next couple of slides on, is a mathematical model for this problem, the problem of creating trajectories on the manifold, which is consistent. So it needs to be well defined. You will see like a solution of this closed loop dynamics needs to exist, and ideally coordinate free. So I would say this is our current problem in power systems, that your behavior should not change if you change coordinates, and you'll see later that this comes as a bonus almost for free. Okay, so the tool we decided to use is the tools of projected dynamical systems. This because for every feasible region, so for example, for our region of a manifold intersected with constraints, if it's sufficiently regular, and that's the case in our case, you can define a tangent cone. A tangent cone is basically, for which you can see the formal definition here, it's basically the set of all directions that keeps you inside the feasible region, right? All directions that you could use as velocity in your trajectory, and you would remain in the feasible region. Okay. Once you define this one, you can actually project a vector field on this cone. Okay, so this projection, because of how the cone is defined, this projection is usually something similar to a quadratic program that you need to solve. And then you can define an initial value problem, so which is a differential inclusion if the projection is not unique, which looks like a usual ODE, right, that you would like to solve. So the closed loop trajectory needs to be something like x dot in the projection on the tangent cone of a vector field that you can design. That's the kind of mathematical object we are going to study here. First thing we would like to check, and we checked, is that this is actually well posed. So under enough sufficiently, under reasonable regularity conditions, a solution to this differential inclusion problem actually exists. And this is the first, and this is the object we are going to study. So notice that here there's still no control design problem. Like regardless of how you control the system, the trajectory or the state of a power system needs to satisfy this differential inclusion if it stays on the manifold and satisfies the constraints, right? So it's not, we are still not at the design phase, but this is really like a well-posedness check on the problem. Things are a little bit more complicated when these domains are actually time varying. I will not cover this one in much detail. You need to extend it to a temporal tangent cone. This is some original result we have done. You can prove that things remain well posed if the sets move, but sufficiently with a limited rate of change. Okay, with some technicalities on top of that, but that's the key idea. So there's this can be extended to time varying setups. And okay, this is all I wanted to say about the trajectories on the manifold. What we proved is that under some conditions, which are relatively weak but relevant for the system, for power systems, it's possible to talk about trajectory of a power system on the manifold of power flow solutions. Okay, these requirements are generically satisfied in power system, but they're not completely trivial. Like if you want to apply, you need to verify them. It's actually it leads to some interesting consequences that if you like, we can discuss later. Okay, now this was only a well-posedness check. Okay, so we can talk about trajectories, closed loop trajectory on the system. How do we get the closed loop trajectory that we want, the one that converges to the solution of the optimum power flow? Well, we need to move from this implicit representation with the power flow equations to an explicit representation where you have inputs and outputs, right? So what you have in practice is that there is a set of things that you can control in the system. There's a steady state map on the system, and then there's an output of the system that you can measure. So now, we can't, this H of UW, it's simply the explicit representation of the manifold. Y is equal to H of UW means that f of x, where x was the entire U and Y, is equal to 0. Okay. Now, if you have this input and output map, then the problem is to design a feedback optimization controller. So a controller that decides U based on Y, that makes sure that the closed loop behavior of the system satisfies our desired specification. So converges to the solution of the optimum power flow while satisfying constraints. Okay, these are the same as before, just rewritten in the explicit form. Now, I mentioned this already, but maybe it's even clearer now. This, from an optimization perspective, it means that we are designing an algorithm, but the algorithm is a dynamical system, right? We're designing an optimization algorithm, but it needs to be a controller for dynamical system. And from a control perspective, people have interpreted some feedback systems as solvers for some optimization problems, but typically just as a reverse engineering kind of step. So here we would like to design them, not to just interpret previous available controllers. Okay, but the way we do it is actually relatively simple. So we started from what is probably the first guess that you would make. How about we take the gradient of the cost function and we try to follow the gradient? So in this notation here, which may look a little bit let me help you parse it. What we are doing, we are taking the gradient. Now the gradient with this input output representation requires you to apply the chain rule. So you have sensitivities of the output with respect to the input times the gradient of the cost function, right? You project it on the tangent cone, and this is the vector field F that I had before. I mean, this is the controller. How about we start from something as simple as that? This would definitely fit in the setup we had before. This is a projected dynamical system. As you can imagine, this goes in the steepest direction of descent for the cost function, but it also remains in the feasible region. And so it's a good candidate for what we are trying to do. Okay. Notice that the input saturation is guaranteed, right? Because we are projecting on the feasible region. I promise you, because I won't cover it, it has all the features you need for robustness, because the only model information here is this little piece here, is the sensitivities, is some linearized input-output relation. So you don't need the full nonlinear model. And the feasibility, staying on the manifold is guaranteed because once you give inputs, the system will respond and the output is going to be on the manifold. Okay. Notice that there is one step that maybe some of you have noticed, but I want to clarify. Here we went from f of x is equal to 0 to an input-output relationship that requires some conditions, right? Some technical conditions to go from an implicit representation of a manifold to an explicit one. in power systems, these conditions are guaranteed. In fact, they actually correspond to very old voltage stability conditions for a power system. If they don't hold, then we have other. And that's actually what we used for the teaser plot at the beginning, to force these kind of conditions, but that's a story for another day. Okay, so now we did, we haven't proved anything yet, right? But we projected the gradient, and we basically started from a gradient descent algorithm, one of the simplest optimization algorithm, iterative algorithms you can think of, and we got a controller, right? You could that's actually the recipe we recommend. Like, you start from any optimization algorithm, iterative optimization algorithm, and by taking the continuous time limit, you get your controller. So you can start from gradient flows, interior point methods, accelerated methods, momentum, accelerated gradient and momentum, saddle point flows. All these methods are good candidates to be taken as the starting point for the design of your controller. Now, if you take the continuous time limit, all these differences become a little bit, they vanish a bit. In continuous time limit, most of these algorithms are either gradient flows with or without momentum, or they are saddle flows. Even Newton flows are just a choice of metric. And then, of course, on top of that, you have the projection. So what we studied is how we can use gradient and saddle flows with and without momentum for this kind of control design problem. Let me start again from the gradient, because that's the one I presented, and then things extend relatively easily to the rest. What do we need to prove now? So that was just very reasonable to take a gradient descent projected on the constraints and see that it drives the system to the solution of the OPF, but we haven't proved anything, right? It's not obvious that this is going to happen. Where is the trouble coming from? The problem is that the physical plant is actually a dynamical system, right? So the output of the physical system of this system you are controlling reacts to the inputs with some dynamics. So consider this simplified case. Here we have the simple gradient descent. Okay, so not even the projection. I will add the projection later. So U dot is simply D with some matrix in front, is the minus the gradient of the cost function. And the plant dynamics give you the output. In this case is X. We don't have, we assume observability. X dot is equal to some f of X and U. Of course, the steady state of this map is the H of U that we're using before, right? But in reality, this is a dynamical system. Now, when you interconnect them, you get the X dot. So the state of the system evolves according to the inputs you're passing, and the input evolves according to your gradient descent law. Again, we have chain rules, so we need the sensitivities in here. Now, that's the object we need to study, right? So we need to study this interconnection here and prove that this converges to the points which are minima of phi of X, subject to the constraints. Okay, so that's the control design problem. This is actually true under some reasonable conditions. So if the physical system is exponentially stable and there exists a Lyapunov function with some rate of convergence, you don't need the expression. You need to know this rate of convergence. You can actually estimate from experiments. And if the cost function has some very weak regularity assumptions, like compact level sets and Lipschitz gradient, then all the trajectories converge to the KKT points of the optimization problem if the gain that you have in front is bounded above by a number, which is, of course, function of this rate of convergence. Okay, so if your optimization algorithm is sufficiently slow and therefore allows the system to react properly, then you actually converge to the solution of the original optimization problem. So you actually have implemented a solver for your optimization problem using the dynamics of the system. Notice that this is a nice solver because in here, your solver doesn't need to know each of you, right? It only needs the sensitivities. In power system, this is particularly impressive. It doesn't need to solve power flow equations at all. It only needs to know sensitivities of the power flow equations, which are a much simpler object. And still, the closed loop system will converge to the solution of the optimal power flow. Okay. You can also prove almost, with some little extra steps that second order conditions on these minima, like strict local minimizers, are connected to asymptotic stability of the closed loop dynamical system, right? So the theorem here only connects equilibria with stationary points. But you can bring, you can step up and you can talk about stability, and you can connect asymptotic stability with minima and not other stationary points like local maxima or other things. Of course, if everything is convex and linear, then everything becomes global. Okay, I won't go through the proof, but if you have seen the proof for singular perturbation analysis, you would recognize some of the tricks here. So the idea is that if you have this H map, you can add it and subtract it to the system. And so you get two systems. One is the physical plant minus the steady state. So what's left here, down here, is actually the residual tracking error. And the optimization algorithm, the fact that you had this piece here is now the optimization algorithm in closed loop with the steady state map, not with the dynamical system. So that's the easy object to study with a disturbance, which is the residual of the dynamics. Okay, once you rearrange things this way, you can actually, the key idea is that you use a Lyapunov function for both parts. So for the optimization algorithms, it's simply the cost function. For the physical plant, we assume we have one. This is only for the proof, right? You don't need to know it in practice to apply it, but for the proof. And then if you evaluate the Lie derivative of this Lyapunov function, you can actually prove that if you mix these two Lyapunov functions properly, then you guarantee that the cost function, this Lyapunov function, is decreasing along the trajectories. And then you have to check some additional requirements and use LaSalle invariance principle and conclude on the stability. Okay. At the very end, it's where you connect LaSalle conditions are actually connected to KKT conditions. Okay, now I've done it for only gradient descent, right? So if you take Q is equal to identity, remember Q was the matrix in front, then you get the the vanilla gradient descent. If you add projection, with some work you can prove it's the same thing. The stability of the interconnected system is not affected by projections, which is good, same bound. If you want to use Newton, then you have to pick this gradient, this gain in front based on the Hessian of the cost function, and you get some slightly different bounds. Nothing too different, but it's a much similar procedure. And in general, you can apply it to any iterative algorithm that you can think of, but not all of them. So, which I think it's interesting, right? Otherwise, it would be a bit of a trivial result if it always works. This analysis tells you that some methods, you should not use them for feedback optimization. For example, subgradient methods or accelerated gradient methods. Why? Because because the conditions of the theorem are not satisfied. But actually, if you try to implement them, you see it's not only a technical reason, they truly don't converge, don't work. So for example, subgradient flows, the projected dynamic, the optimization dynamics would be this subgradient update, a differential inclusion, because the subgradient is a set. You can check that the Lipschitz assumption on the gradient is violated, so the theorem does not apply. But actually, if you implement it, you see that as an optimization algorithm, it works, but in closed loop with the dynamics of the system, it doesn't converge. Okay, so subgradient methods are not a good idea for feedback optimization. Momentum-based feedback optimization requires some particular care. Gradient flow with momentum are gradient flows where U dot is driven by an auxiliary variable Z, and Z dot is driven by some damping plus the gradient, right? It turns out that they need to trade off gain and damping in the proper way to get stability. And if you don't do it, the theorem fails, but actually the system fails in reality. So for example, in accelerated gradients, typically people decrease the amount of damping to make the system faster in time. But you can see that because this violates the requirement of the theorem, you truly don't have convergence. Again, the red line is showing that as an optimization algorithm, this works very well. But as a controller, you cannot take an accelerated gradient flow, convert it into a controller, and apply it in closed loop to the system because it won't work. Okay. Anything else, the theorem can be applied. So if you take any other dynamic where you have even with some memory, right? U dot equal to something and Z dot is equal to something else driven by the output of the system, you can extend the theorem. I mean, the more you extend it, the less readable it becomes, but the procedure is the same. You would get an upper bound on how fast on the gain in front of your controller. And if you satisfy that, then you guarantee asymptotic stability. So to conclude this part here, and actually I'm basically done, the key problem is to study the interconnection of the plant dynamics with the optimization dynamics. We were able to design sufficient stability condition, which require very weak assumption on the plant, basically stability of the plant. So we need only to know that there is a steady state, and we need to know the steady state sensitivities. And very weak assumption on the cost. We just need to know that it's as a Lipschitz gradient. Not even convexity is required. And then the bound you get might be a bit conservative, but it really literally requires no assumption on the plant, and it's particularly useful for design because it can be applied to any optimization algorithm that you can think, and that you want to bring into the domain of cyber physical systems, like of control instead of algorithms in your computer. The analysis is really agnostic of the kind of iterative algorithms you're applying, as long as you can repeat that LaSalle reasoning on the vector field that you want to implement. Just to go back to the original motivation, if you apply this one to power systems, you can actually see that things behave as we are expecting. So in this case, this is another power system, not the same as before. In this case, everything is relatively stable in time, but at some point you see here, one line, you can actually see better here, one line drops because it's disconnected, there's a fault, right? And here, a generator is disconnected. So the system needs to go to a new set point. And you can see here, there is a transient in both cases, but the system is stable and can actually track the dashed black line, which is the optimum. Okay. It turns out that I told before that these results are only sufficient conditions and they're conservative. It's really a bit application specific. It's not so conservative for power systems. Like if you take twice the bound, it's actually still stable, but if you take 10 times the bound, it's not stable, which for singular perturbation analysis kind of things is actually good. I know people would observe much, it's not too conservative in practice. Okay, so with this one, I'd like to conclude. What I've shown you is that you can use feedback control to solve constraint optimization problems, okay? This requires a little bit of care. It requires a mathematical framework of projected dynamical systems, at least that's the one we used, and I think it served us well, because that allows you to prove that things are well posed, a solution exists, even if constraints are time varying, regions are complicated, and so on. Once you set up the problem like that, you can actually prove convergence of the interconnection of a physical plant with your optimization routine that you get from your preferred iterative method. In terms of applications, it turns out that this is seems very effective for power system operation. And so, well, for a number of reasons which are a bit application specific, for example, the lack, the robustness to model mismatch, which is something they care about a lot. The fact that you have feasibility of the entire trajectory and not only of the endpoint, which is also interesting. And the fact that you are free to design your own optimization and constraints, which looks like a unified approach to all these real-time operation problems that I described at the beginning. And that's the reason why right now we move to, we are validating this as a solution for true power system operations with RTE France, which is the operator in France, under this unicorn project. At the same time, and that's why I'm also happy to reach a different or a diverse audience, is we are also, you've seen most of the analysis here doesn't really require power system assumptions or a power system setup. We are looking into some other application domains. The idea is that you need a problem where you want to steer a physical system to an optimal point. You care about your specification come as a optimization or cost specification of the endpoint or the point you're going to track, but most importantly, constraints on what you can do in the trajectory with some degree of robustness. For now, we have looked at some problems. An interesting one is in medical applications for anesthesia. I think we had a bit of fun in a semester project for that, but I would be happy to discuss your views on that. Okay, this concludes the talk. Of course, this was the work of many people. Adrian, that just finished his PhD, Lucas, that started a couple of years ago and is in the middle of it, and Gabriela Hug from Power System Lab, and Florian Dorfler from Automatic Control Lab. Thank you.
Thank you, Saverio. Very cool talk.
Thanks.
Are there questions from the audience?
Well, more than a question is a comment, right? So you were talking about application domains. Clearly, one of our preferred application domains is the transportation systems, right? So, and I could see many parallels between power systems and say transportation network, things like that. Actually, I think that with the very first students doing this, we actually talked to Florian, and we did something together back in the day. So have you thought about that application at all? Probably you have that.
Sure. So there's connections, of course. The features that I see, like where there is the most overlap, is the fact that the role played by constraints. So, for example, if you have a given use of the traffic infrastructure, a given amount of flow on the graph of road connections, and you want to reach another configuration because it's optimal in some sense, you can't just go from point A to point B without considering the trajectory it takes you from this configuration to the next one, because all your models are only valid as long as congestion is not critical, as long as there's a maximum amount of cars that can fit on a road, there's a maximum speed at which things change. And so the fact that you actually have a recipe that can take you that can steer the system towards optimality with a focus on constraints, I think it would be a core feature. And the other thing that I think would work well is that it's a model robustness, because solving here our controller is able to steer a system to a solution of an OPF without solving power flow equations. We need only sensitivities. We need to know that by increasing some generation, this power line flow is going to raise or lower, right? And my, from at least the, my non-expert view, something similar could happen in traffic, where computing the state of the system given boundary conditions is a much trickier problem than telling me that if you put a red light, if you increase the duty cycle of a red light, then then the flow is going to increase or decrease. That seems to be something for which you have much stronger and robust understanding of the model than doing a feed-forward simulation of what's going to happen in the system. So yes,
what's the trick by which you can say, because essentially you're saying that you can use only local information, right? But then you still have some form of non-local, I don't know if you can say global, convergence, right? So what's the trick?
The trick is that we apply every iteration. So you could not solve this one if you take our controller, and if it's not in closed loop with the system, it simply tells you in which directions to move. Only when you apply to the system actually reveals a little bit of itself by giving you the next measurement.
Okay, so then you're saying, so is a sequence of local information. So essentially, you're replacing this, just replacing using local information to have some non-local effect. And then you're saying, okay, so we use a sequence of local information, right?
Yes. I mean, the system is our power flow solver, right?
Something more than that you need. I mean, that's the difference between, okay, because in a sense you have some form of control Lyapunov function, right? At the end of the day.
Yes. So.
And then you're using this function, and then you are, I think that you do some form of dynamic extension, blah blah. But then, you had to go down some gradient of some function that can be a Lyapunov function for the closed loop system, right?
Sure.
So, but then how do I know? I mean, what do I need for my optimization, my cost function, whatever, to be such a control Lyapunov function? I think it's not obvious that.
No, it's not obvious, but if you take the point of view of control Lyapunov functions and design of controllers here, you have a number of assumptions, of hidden assumptions here that actually help you. For example, the physical plant is actually a stable plant. And so when you construct a combined Lyapunov function, you don't need to, it's not a stabilization problem.
Right. So in a sense, I'm kind of trying to figure out, thinking of translating this from the power networks to the transportation networks, what are the, because what are the things that need to happen, right? So what are all these assumptions, hidden or not, right? That need to be true.
I would start from this assumption. I would start on the assumption that given your input, you're going to observe an output. So the system is going to be stable. It's actually some incremental stability, but there's going to be an H of U, right? There's going to be a steady state map. So there are many systems, for example, those that include queues in general, where given an input, you get a ramp, or you get, you don't get a nice steady state. So there is at least one unstable or marginally stable dynamic in the physical plant. And in that case, that requires a little bit of care, because it's because the core assumption here is that I give some input and I observe the output, and the output is a steady state. Is not the system actually reaches this or exponentially converges to this steady state map. Not that we have tried, but when we were looking, for example, at problems in power system where we had batteries, which, it seems that if you have anything where it is storage, then you need to be a little bit careful. And if traffic system include that, like in the sense that your input is a flow, but this creates congestion, as in, a queue growing, then you might need to rearrange things a bit.
So some kind of like a valve to let off steam or something, right?
Yes, so, exactly. So it cannot be.
Don't blow up. Okay.
You can stabilize things and then use an outer loop as your references. But I'm just saying it's not trivial. It's not completely one-to-one.
Thank you.
No, thanks, Emilia, for the comments.
Any other question? Nope.
Just to ask one question.
Mm-hmm.
Can you say something about how do you talk with in this case, these are private companies or public companies? Like, what's the social process to go from algorithm to implementation in your experience?
Oh, for this kind so we're working with a transmission system operator, right? RT is the transmission system operator, which is a little bit of a weird, which has some strange objectives. So, for example, most people when talking about OPF talk about the economic cost of running the system. But this is, TSOs, transmission system operators, are completely transparent to generation cost. Like whatever generation costs, they charge the consumers for that, right? So what they care about, it's mostly safety. They of the kind of emergency measure they can take on the system. Some of them are incredibly cheap, like controlling some set points. And some of them are incredibly expensive, like 3 orders of magnitude more expensive, like disconnecting a load. And so for their point of view, the reason why things are, most of these procedures are mediated by a human is because a human needs to make sure any step is kind of reasonable and acceptable and complies with what are their principles and their commitment to in their contracts, right? In this sense, at least in the conversation we have, they tend to like simple optimization algorithms. Like if you say it's a gradient with projection on the constraints, you won't see them asking for a faster gradient, a faster method which has momentum and acceleration, because the gradient is quite well explained. Like it's doing probably the best possible step towards safety, and that's not the direction they would push. Like they will not push in the direction of the performance of the optimization algorithms for tracking. They would rather see what happens when you have constraints, when constraints move, when the problem is unfeasible. I think it's, I know, my impression is that this is getting like a bit of a recurring theme. You can automate this thing, but as long as you can explain what you're doing. And in the worst case, you'll have an operator that looks at what your optimization algorithm is recommending and press a button to say, yes, I mean, it seems good to me. I think this is, they're not too unwilling to experiment things. We're now working with them on a model for a Bloco area, which is a part north of Paris, where they already deployed some automation, and they're at simulation level, they're happy to experiment and see if they can be coordinated a bit.
Thank you. Thank you.
Mm-hmm.
Great. Thank you very much, Saverio, for the great talk. I think you gave your coordinates if people want to reach you.
Of course, yes. And there's a bit on my website, but I'm always one message away if you want to get in touch.
Very good. Thank you very much.
Thanks a lot, everybody.
And thank you all for participating. See you next week.